Yo, what's good, Anophel crew? It's your boy, back with another banger on the Anophel channel. Today, we are diving deep into race conditions in Golang. We're not just gonna talk about them, we're gonna cause some chaos, break our programs and purpose, and then fix them like pros, using a bunch of cool techniques. Why should you care? Because race conditions are sneaky bugs that can tank your app in production, and we're gonna learn why they happen and how to stop them. So, if you're pumped to level up your Go concurrency game, grab a snack, hit that subscribe button for more Anophel goodness, and let's dive in. Alright, let's break it down. A race condition is like two people trying to write on the same whiteboard at the exact same time. Things get messy and you end up with gibberish. In Go, it happens when two or more coroutines, those lightweight threads Go is famous for, trying to read and write the same shared data like a variable without any rules. The result, it depends on who gets there first, and that's a problem. Here's the kicker. Go's scheduler, the thing that decides which coroutine runs when, is totally unpredictable. It's like a DJ switching tracks at random. So, if two coroutines hit the same memory spot without coordination, you get a race condition. And the worst part, these bugs can hide during testing and only pop up when your app's live in production. Ouch! To make it real, let's cause a race conditions or slaves and see what happens. Time to get our hands dirty. We're gonna write a simple Go program that spawns 1000 coroutines. It's trying to increment the shared counter. Spoiler, it's gonna go wrong, and we'll use Go race detector to catch it. Here's the code we're working with. This program looks simple, but it's a ticking time bomb. We're launching 1000 coroutines, each trying to do counter plus plus. But counter plus plus isn't one operation, it's a tree. Read the current value of counter, add 1 to it, write the new value back. If two coroutines do this at the same time, they might boost read counter as, say, 42, add 1 to get 43, and write 43 back. One increment gets lost. So, I ran this simple app, and we see final counter is 997, and I try again and we see final counter is 997. That's why the final counter is often less than 1000. So what's going wrong here? Counter plus plus isn't atomic. It's not one indivisible operation. It's like two chefs trying to add sugar to the same cake mix without checking what the other is doing. The result? A mess. To prove it's a race condition, let's use Go's race detector. I run this command, go run. I use dash race flag and file name mine.go, mine.go, and enter. You'll see a screen warning like this tells us exactly where the unsynchronized access happened. Cool. Right. Now let's fix it. Alright, we broke it, now let's fix it. There are a few ways to handle race conditions in Go. and we're gonna cover 3 using a sync.Mutex, sync/atomic, and channels. Each has its own vibe. So let's check them out. Solution 1. We use using sync.Mutex. First, we declare the mutex. For create a mutex, I use var mu sync.Mutex. So we know we should be wrap the critical section. So I go inside of coroutine, okay, and call mu.log. I call mu.log function before of counter plus plus, and after of counter plus plus I call mu.unlog function. So I want run it before. Now the counter should hit 1000 or close depending on timing. I run it and we see 1000, and I want I use a test with race detector. So I write go run dash race flag and write file name main.go and enter to confirm no race conditions, and we see 1000. A mutex is like a bathroom key. Only one person coroutine can have it at a time. When a coroutine calls mu.log function, it grabs the key and increments counter. Other coroutines have to wait until it calls mu.unlog function. This ensures only one coroutine messes with counter at a time, so no increments get lost. This solution is super reliable. The mutex makes sure only one coroutine can touch counter at a time. Solution 2. Using sync/atomic. We know for this solution we should be change type of counter to int32, and I change type of counter to int32 because atomic ops work with specific types. And I go inside of coroutine and I remove counter plus plus and write atomic, and I call add int32 function, and for first command for first argument I pass address of counter, and for second command second argument I pass 1. So I run this app and we see 1000 for counter. So I use race detector and I run this command go run dash race main.go. We see 1000 and no warning we see. Okay. Sync/atomic is like a ninja. It's super fast and handles increments at the CPU level. Atomic.add int32 function does the read add write in one unbreakable step. No logs, no waiting, just pure speed. It's perfect for simple operations like incrementing. This is the high performance option. Atomic ops are faster than mutex because they don't need to coordinate coroutines. The CPU does the heavy lifting, but it's only for simple stuff like adding number. Solution 3. Using channels. So for this solution I should be create channel. So I remove first I remove a counter variable and I define with this syntax counter equal 0. Okay. and I should be create a channel. Okay, and I create channel and I use make function for create channel. This channel is integer. Okay, and I write int, and no, I cut this goroutine and cut it, and I define it or paste it outside of loop, and I remove inside of goroutine I remove counter plus plus. So I should be create a new loop in this for reads from channel and updates counter. Okay, so I define new loop, and I define new variable v range channel, and I use counter plus equal v. Okay, so in outside loop I should be send increments. Okay, in this loop I send 1 to channel 1000 times. Okay, for this I define ch channel, and I write this syntax, and I send it 1. Okay, to this channel. Okay, that send increments. Okay, and I should be close the channel. Okay, I define or I call close, and I pass it channel. Okay, this signals the worker to stop. So I run this, and we should be see 1000, and we see 1000. Okay, and I want test with trace detector, and I run it, and we should be see no warning and no races. So yes, we see 1000. Okay, channels are Go's way of saying let's keep things organized. We send increments once through a channel, and only one routine, the worker, updates counter. It's like passing notes to a single accountant who updates the ledger. No conflicts, no races. Channels are super Go idiomatic. They are not always the fastest, but they make your code clean and safe. This pattern, where one routine owns the data, is a concurrency superpower. Now let's talk about a real world scenario, a shared map. Maps in Go are not thread safe, so if multiple routines write to one without protection, it's gonna crash. Let's see it happen. Let's start with the import and main function. We import fmt for printing and time to push the main routine. Now I'll declare a map that holds string keys and int values. Next, I'll launch 100 routines that each write to the map with a unique key. Here, each routine receives its own copy of I as an argument to avoid the common closure trap, but all of them are waiting to the same map M. To give coroutine time to finish, I'll push the main function using time.sleep. This code is a disaster waiting to happen. We're launching 100 coroutines, each writing to the same map. Go maps aren't built for concurrent writes, so this will panic. It's like 100 people trying to edit the same Google Doc at once. Chaos. Run this and you'll probably get a panic. Fatal error. Concurrent map writes. That's code telling you, nope, can't do that. Let's fix it two ways. So first way we use sync.Mutex. Okay, we first add mutex. I declare var mu sync.Mutex and I go inside of Golang and protect map rights with mu buffer of this buffer of map. I use mu.log. I call log function and after I write mu.unlog. Okay, and I run this and no crash. Okay, and I come in here and I run go run dash trace main.go and we'll see no crash. Just like with the counter, the mutex ensures only one coroutine writes to the map at a time. It's like giving one person the pen to write in the shared notebook while others wait. The mutex makes the map safe, no more crashes, and the race detector is happy. So second way, using sync.map. In this solution, I remove this map and declare sync.map. Okay, I declare with var m sync.map. Okay, and inside of Golang, before after of m and I store I use a store. Okay, and store this map store. Okay, and fix it like it. Okay, and remove this and this. Okay, and this equal I remove and I run it. Now it's clean and it's work, no fatal error or panic error, and I test with race detector and it's clean. Okay. Sync.map is a special map built for concurrency. It's optimized for cases where you have lots of reads and fewer writes. Store is like a safe map at key equals value that handles all the concurrency for you. Sync.map is the easy button for you for concurrency map. It's built for this exact problem. So if you're dealing with with shared maps, it's often the way to go. Before we wrap up, let's hit some big ideas you need to understand. Non-atomic operations. Stuff like counter plus plus isn't one step, it's a multiple, which is why race happen. Goes scheduler. It's a random, so you cannot predict Golang order. Don't rely on luck. Mutexes. They are like bouncers, keeping things orderly but can slow things down. Atomic ops. Fast and furious, but only for simple types like integers. Channels. Goes secret source for clean, safe concurrency. Use them to serialize access. Master this and you'll be Concurrency Ninja and the Anophel channel. And that's a wrap, Anophel fam. We didn't just talk about race conditions. We caused them, dedicated them with Go race detector, and fixed them with pro level techniques like mutex, atomic, and channels. Now you're ready to tackle concurrency like a boss. If you love this deep dive, smash that like button, subscribe to Anophel for more Go tutorials, and drop a comment. Tell me about a concurrency bug you forget or what you wanna see next. Oh, and share this video with your coding buddies. Let's grow the Anophel crew. Catch you in the next one. Peace out.